So we can study how the particles in these crystals are arranged. Now we're going to look at the different types of arrangements. When we talk about a crystalline lattice, we're talking about the regular arrangement of atoms within a crystalline solid. Those could be molecules or ions as well. The particles are going to combine and arrange themselves in a way that minimizes their energy. So they're trying to maximize any attractions and minimize any repulsions. So you've got this huge array of gazillions and gazillions of atoms. We're going to focus down into what's called a unit cell. That's the smallest divisible unit of a crystal that when you repeat it in 3 dimensions, reproduces the entire crystal lattice. So here we're looking at a 2-dimensional lattice, and the smallest piece that you could repeat and reproduce everything would be this square right here. So you take this square and you replicate it over here and over here and over here, etc. And so this is the smallest piece that describes that lattice. Does that make sense? It's called a unit cell. We draw circles to represent the lattice points. Those are going to be occupied by an atom, an ion, or a molecule. So this dark square here is the unit cell for that lattice. Any questions? So there are different types of unit cells. We're only going to talk about cubic unit cells and one hexagonal. So here's a cubic unit cell. And what makes it cubic is that the length of each side is the same. So A equals B equals C. So all of the lengths, it's a cube. The length, width, height, all the same. And all of the angles are 90 degrees. And then these give you some of the other ones. So you can have tetragonal or tetragonal, not sure. So there you've got 2 sides of the same length, but the third is different and still all right angles. Rhombohedral, here you've got A equals B equals C, but now the angles are not equal to 90. So that's, all cockeyed and skewed. So these are all different types. This is the cubic is what we're going to be looking at. And when we look at these unit cells, this is just, again, the tip of the iceberg. So we're going to just look at the simple parts and kind of show you that there's more complex things, but we're not going to ask you to really do anything with the complex stuff. We're just going to look at each atom in the structure is identical to the other atoms. Okay? There will be different colors in the pictures we're going to look at. Those are just to help us visualize what's going on, but all of them are the same type of atom. We talk about something called coordination number. That's the number of atoms that each atom is in direct contact with. How many closest neighbors does it have? And depending on how the atoms are arranged, that number can vary. It's the number of atoms with which a given atom can interact strongly. Because all of these interactions are only strong at very short distances. Another thing we talk about is packing efficiency. It's defined as the percentage of the volume of the unit cell that's occupied by the spheres, the atoms. So if you have a high packing efficiency, there's very little empty space in that unit cell. A low packing efficiency is going to have more empty space. And these go hand in hand. If you have a high coordination number, you're going to have a larger packing efficiency. So these are 3 cubic cells. Simple cubic, body-centered cubic, and face-centered cubic. This is just kind of an overview. We see the coordination numbers are different here, 6, 8, and 12. And the packing efficiency, 52, 68, 74%, that increases as the coordination number increases. We're going to look at each of these individually. So the simple cubic unit cell has 1 atom centered at each corner. So we've got a cube here, and here's the center of 1 atom at this point, and there, and there, and there. And so the atoms are going to touch along the edges of this cube. And if the radius of the atom is r, then the length of the side is 2 times the radius. Right? So the length of the cube side is 2r. One of these units contains 1 atom. It contains an eighth of 8 different atoms, right? You've got 1, 2, 3, 4, 5, 6, 7, 8. So there's 8 atoms, but you only have an eighth of each of them, and so overall it's 1 atom. Any questions? So we draw this out in different ways. It's hard to visualize 3-dimensional things on a 2-dimensional screen and when you can't see through them, right? So this is just looking at the individual unit cell. Here, this is looking at the 8 atoms that are part of the unit cell, and the little cube that's drawn in here is the unit cell, because we're looking at the center of the atoms. And then this is more of an expanded form, showing us how the coordination number is 6. So here's one unit cell up here, and if we look at this one in the corner, we see that it's in direct contact with 1, 2, 3, 4, 5, 6. It's touching 6 other atoms. So the coordination number is 6. Any questions? So here's a practice problem. Calculate the packing efficiency of the 2-dimensional lattice shown here. Calculate the packing efficiency. Well, what is the packing efficiency? It's the percentage of the whole thing that's occupied by the spheres or the atoms, right? So this is 2-dimensional, so we're talking areas instead of volumes. So it's the area of the spheres divided by the area of the cell times 100. So if we're looking at this unit outlined here, let's call the radius of an atom r. Okay? And I'll make another one down here. Right? So we've got something, well, that's not very good. Something like that, right? This is r, the radius of an atom. So what's the length of the side? 2r. So what's the area of the square? 4r squared. So the area of the cell is 2r, the quantity squared. Right? 2r times 2r. Everybody okay with that? Now, how much of that is actually occupied by the spheres? Well, this is 1/4, right, of a circle, and this is 1/4 of a circle, and 1/4 of a circle, and 1/4 of a circle, right? So there's one full circle in that square. If you cut these out and put them together, you could make a circle, right? So there's one circle. What's the area of the circle? Pi r squared, right? So the area is pi r squared. So we got one circle in there. The area of the circle is pi r squared. The area of the square is the length times the width. Okay with that? So this is the area of the sphere, with our pieces of the spheres, divided by the area of the cell, times 100%. And so then we just need to simplify this. So we've got pi r squared in the numerator and 4r squared in the denominator times 100. So the r squareds cancel out. We got pi, there's my pi button. Pi divided by 4 times 100. Why is it showing me that? It's showing me 25 pi. I don't want 25 pi. $78 point what? 5. Okay, that's fine. So 78.53%, 78%. I have to have a conversation with my calculator. 25 pi. I can do that part in my head. Any questions? This is geometry, isn't it? Yeah. Yeah. I thought I was never going to have to use that again. Calculus, probably not that useful in everyday life. Algebra and geometry, they do come up. They really do. Okay, on to the next unit cell. Body-centered cubic unit cell. So the body-centered cubic unit cell has one atom in the center and then atoms at each corner. Okay, so now the atoms along the edge are not actually touching because there's this one in the middle that's kind of pushing them apart. But the atoms do touch at a diagonal through the cube. Okay, so from one corner to the opposite corner of the cube, not along a side even, but from one corner to the opposite corner of the cube. So that's a little harder to figure out what the angle or the length of the side is, right? The previous one, it was easy. It was just 2r. Well, there's the derivation for those of you that like that sort of thing. The length of the side equals 4 times the radius divided by the square root of 3. There's a Pythagorean theorem involved in there. So this is the cutaway version of the unit cell. Here is where we're showing all of the atoms on the corner, the entire atoms. But again, it's 1/8 of each of those purple ones plus the gold one in the middle. And the gold and purple colors are just to help us see, okay, this one's in the middle and these are on the edges. They would actually be the same atoms. So this cell has one center at the atom and 1/8 of 8 atoms, and so this is a total of 2 atoms in a cell instead of just 1. You see that? And then when we talk about coordination number, here we've got our cubic unit cell, and we've got parts of it reproduced over here. And so this guy here is going to be touching 8 different ones instead of, what was the last one? 6. The last one was 6. And so the packing efficiency has gone up. It's 68% now. So we could do a problem like this. An atom has a radius of 138 picometers and crystallizes in the body-centered cubic unit cell. What's the volume of the unit cell in cubic centimeters? Well, let's go back and find out what that's not what I wanted. We're going to need this guy right down here. 4r over the square root of 3. R over the square root of 3. That's the length of a side of this unit cell. The atoms in this cell have radii of 138 picometers. And so they're asking us what's the volume of the cell. So we've got a cube, and the side is L. The volume of the cube would be L cubed. right? Length times width times height. So the volume is going to equal L cubed. And L is 4R over the square root of 3. We want to cube that. So we know what R is. It's given to us in picometers. And they're asking for the volume in cubic centimeters. I can do unit conversions with cubed units, but I'd rather just do it with a straight unit. I'd rather put this into centimeters before I stick it in this equation and cube it. That's simpler to me. So I'm going to take 138 picometers. What does pico mean? Times 10 to the minus 12. So instead of pico, I'm going to write times 10 to the minus 12 meters. And then I want to convert that to centimeters. Centimeters on top, meters on the bottom. Then I ask myself, what does centi mean? Centi is 10 to the minus 2. Okay, so that gives me 138 times 10 to the minus 10 centimeters. I did that in my head. You can do it on the calculator too. But if I'm dividing by 10 to the minus 2, that's adding 2 to this, and I get 10 minus 10. So I'm going to take 4 times 138 times 10 to the minus 10 centimeters, and divide by the square root of 3, and cube the whole thing. So, you have to figure out how your calculator wants you to talk to it about this. I'm going to do 4 times 138 EE minus 10 divided by square root of 3. And then I'm going to raise that to the third power. Well, I think that might want some parentheses. Having a conversation with my calculator here. It's really more like an argument. There we go. Okay, I'm getting 3.24 times 10 to the minus 23rd. Cubic centimeters. I heard a noise that I took as an affirmation of my calculation. Anybody else get that number? Okay. That's a really small number. Is that okay? It's more than okay. We're talking about a unit cell that has how many atoms in it? 2 atoms. It's going to be small, crazy small, okay? Any questions? So we did simple and body-centered, and the third cubic cell is the face-centered cubic unit cell. So here we have an atom at each corner again, but now instead of one in the center, we have an atom centered on each face of the cube. So the faces, there's 6 faces, and so this is face-centered as opposed to body-centered. So here we have the atoms touching diagonally along one face of the cube. So the calculation here is a little simpler, but it's still not very nice. The length of one side is 2 times the square root of 2 times r. And I don't expect you to remember that sort of thing. Here are the more blown up diagrams. So here we've got looking at how many atoms are in here. Well, you've got the corners. That adds up to 1 atom. And then on each face, you have half of an atom. There are 6 faces, so that's a total of 3. So in the whole unit cell, you have 4 atoms. So the corners are each 1/8, and so 8 corners times 1/8 is 1. So the purple, if you took all of those sections and stuck them together, they'd make 1 purple sphere. Does that make sense? And then this face-centered, each face of the cube, there's 6 faces. Each face has an atom centered on it. So it's got half of an atom. The other half of that atom is in the next unit cell. So there's half here and half there. That would make another atom. Half there, half on the back, half on this side, half on the bottom. That accounts for 3 more atoms. So a total of 4 atoms. The coordination number is 12. Yeah, good luck seeing that in there. I can't even see it in there, but it's true. It's true. And the packing efficiency is 74%. Any questions? So let's do a calculation on this one. Chromium crystallizes with a body-centered cubic unit cell. The radius of a chromium atom is 125 picometers. Calculate the density of solid crystalline chromium in grams per cubic centimeter. Well, this is the unit cell. The length of a side is 2 times the square root of 2 times r. Length of a side equals 2 square root of 2 times r. Okay, so there's not just a formula to solve problems like this. You have to be able to think about it. So here we've got our cell, and the length of the side is L, and so we know that the volume would be L cubed. And this is what L equals right up here. We know what R is. R is the radius of the cell. It's 125 picometers. So I'm just kind of writing down stuff I know. They want the density. What do I need to calculate the density? I need the mass and the volume, right? So density equals mass divided by volume. You can choose any quantity of this to do. I'm going to choose to do 1 unit cell. I'm going to find the mass of the unit cell, and I'm going to find the volume of the unit cell. How many atoms are in a body-centered cubic unit cell? Do you see where I screwed up? This is not face-centered. This is body-centered. I've got the L for the face-centered. That would be a problem. So it wasn't that. Remember what it was? No, it was something over the square root of 3, 4r. Okay. So make sure that you're using the right unit cell. So we can calculate the volume using this equation and the known radius. How do we know the mass of that? We know the molar mass of chromium, right? How many atoms are in this body-centered cubic unit cell? Body-centered, 2, right? That is confusing. Well, body-centered is where there's 1 in the body of the cell, 1 in the middle, and then the edges. So that's 2. Face-centered is 4. So the mass is the mass of 2 atoms. Let's do that one first because that one's different. So we want the mass of 2 atoms of chromium. Well, we've got the molar mass of 1 mole, right? So chromium, 51.9961. If you round that to 4 sig figs, that's 52.00. 52.0000 grams per 1 mole, but we don't have a mole, we have atoms. How many atoms in a mole? Avogadro's number. So instead of writing a mole here, I'm going to write 6.022 times 10 to the 23rd atoms. Everybody okay with that? It's beautiful, isn't it? Okay, so I've got 2 times 52 divided by 6.022 EE23. I'm going to get 1.727. Now, that 2 atoms is exact. My molar mass here I rounded to 4. Avogadro's number was rounded to 4. So I should keep 4. I've got 4 significant figures, and then I want to keep 2 extras. It's not going to matter this time because they're zeros, but still, the principle of it. Times 10 to the minus 22 grams. 2 atoms of chromium don't weigh very much. It's okay, their volume's going to be pretty small too. So that's the mass. The mass of 1 unit cell. 1.727 times 10 to the minus 22 grams. So the volume is the length of this unit cube cubed. So it's 4r, don't make that look like a pi, 4r over the square root of 3 cubed. Well, again, the radius is given in picometers because that's a great unit for the radius of an atom, but we're going to need centimeters cubed. So I'm going to do that same crazy thing I did before. So 125 picometers equals 125 times 10 to the minus 12 meters. Just writing in the numerical meaning of pico. And then I convert to centimeters, 1 centimeter per 10 to the minus 2 meters. So I come up with 125 times 10 to the minus 10th centimeters for the radius. You can do that other ways. I won't judge. So 125 times 10 to the minus 10 centimeters. And that's divided by the square root of 3. And then we have to cube that whole business. So I'm going to do open parentheses 4 times 125 EE minus 10 divided by square root of 3, close parentheses. Well, actually, I need to move the cursor over to get out of that square root thing. Close the parentheses and raise to the 3rd power. 2.40. We had 3 sig figs, so we want to have 3 sig figs and keep 2 extras to avoid rounding errors. 10 to the minus 23rd cubic centimeters. Anybody else get that number? So that is the volume, so I'm going to divide by that. 2.4056 times 10 to the minus 23rd cubic centimeters. So I've got 1.72700 times 10 to the minus 22 divided by 2.4056 times 10 to the minus 23. And I come up with, after all that craziness, I should have 3 sig figs here, so it's going to round to 7.18 grams per cubic centimeter. Is that a reasonable density for a metal? Yeah. Water has a density of 1. I happen to remember, because I use it so often, that mercury has a density of 13.6. So 7 for chromium, very reasonable. If you had 1,000, or if you had 0.05, or 10 to the minus 52, or something like that, those would be crazy. Any questions? The density of chromium is going to depend on how the individual atoms are arranged. Some elements can form more than one type of a crystalline lattice, and that will affect the density because the packing efficiencies are different. Any questions? So those were cubic unit cells. Another way to think about crystal structures is to think about layers of atoms. And this is not unlike stacking marbles into a box or oranges or other spherical objects into a box. There are different ways that they can be packed in. So the simple cubic structure is where we have a layer of atoms, and on top of that layer, they're lining up exactly. So the second layer, this atom lines up directly with the one below. This lines up directly with the one below. This is not how things are going to naturally line up in a box, though, because the marbles or the spheres are going to tend to fall into the little divots in the lower layer. You can get them to do this, but you have to work at it. There's a lot of empty space in here. Okay. More efficient packing is when you let the rows be offset from each other. Okay, what that other one was doing, let's see, what would be the best way to do this? Do it like that. The other one was going like this. See how they're lining up in a grid? They're making rows this way and this way. This is more efficient because now we've taken this row and scooched it down or up a little bit, and so they can nestle closer together. You see that? So this is going to be more efficient. We've got a row that's moved over half of an atom, and so they'll get closer together in any one layer. Then we have to look at how do we put the layers together. So here's layer A, and we can put layer B on top of it and move it over half so that it's moved over this way half and down this way half, so that this is sitting in this little hole formed by these 3 atoms. Can you visualize that? So there's a blue sphere in each of these little divots. So that is called a closest pack structure, because it's the closest that you can get them. There's 2 different ways you can line them up and have that closest pack structure. They both have packing efficiencies of 74%, and the coordination number will be 12 for both of them. The first one is called the hexagonal closest packed. This is not a cubic unit cell, it's a hexagonal unit cell. The difference between these two that we're going to talk about is the alignment of the third layer. So the first layer of atoms, the second layer of atoms, we talked about how that goes on, and then the third layer is going on lined up directly with the first layer. So the third layer, this sphere, is right on top of the first sphere in the first layer. So this would be a pattern of A, B, A. The third layer is aligned with the first layer. The unit cell here is hexagonal and not cubic. So it's called hexagonal closest packing. So here is a unit cell, and you see that it's not a cube, it's hexagonal, right? So actually that's not the unit cell. This is the unit cell right here, but you get the idea. It makes a hexagon. The other one is called cubic closest packing. And here you have layer A, layer B, and then layer C is not directly the same as layer A. It's offset. So here they're showing you 2 lighter red balls and 1 darker. And here it's flipped around the other way. And this is identical to the face-centered cubic unit cell. It's just a different way of thinking about how they're packing together. But this is a cubic cell. It's called cubic closest packing. So cubic closest packing and face-centered cubic unit cell, exactly the same thing. That's not confusing at all, is it? So if you look at it in terms of layers of atoms, there's the green one, and here's the second layer, and the third layer is not the same. So this is an ABC pattern. And there's this, the fourth layer is the same as the first one. So you can visualize the 4 layers going together. Then to look at the cube, you have to angle this on its side and do some chopping. And there's that face-centered cubic. That's not confusing at all, is it? Wow. Just keep breathing in and out. It's okay.